In chapter 14, we're going to look at the concepts of acids and bases, and in this first part, we're just going to basically define what we're talking about when we talk about an acid or a base. Now, you may be familiar with popular science depiction of acids and bases. So, for example, in spy movies and thrillers, very often an agent will have a container of acid secreted away somewhere on their person that they can use to dissolve metal bars of a prison cell. This is a little bit of an exaggeration of the abilities of acid as far as how quickly it works, but it does give us some idea. There is some basis in reality for that depiction of acids. A place where you're probably more familiar with acids is maybe in your everyday life, in the foods that you eat. So for example, the candy called Sour Patch Kids, or any of these super sour candies, or a lemon, anything like that. When you first put it in your mouth, the first sensation you get is sour. Now, where does that sour taste come from? Well, in the candy, Sour Patch Kids, that taste is coming from this white coating that's on the outside of the candy that's a mixture of acids, citric and tartaric acid. If you were to take that candy and wash that coating off, you wouldn't have that sour sensation when you ate it. It would just be a sweet candy. What's happening is the citric and tartaric acids in that Sour Patch Kid combine with the water in your mouth in the form of saliva, and it produces protons or hydrogen ions. Okay? So when we talk about these H+ ions, hydrogen ions, those are also called protons. And what happens is those protons react with protein molecules on your tongue, and that sends an electrical signal to your brain. It causes the protein molecules to change shape, that signal gets sent, and your brain registers that as a sour taste. All right, so let's go back to that idea of acid dissolving those bars. Okay, so James Bond, for example, often carries this gold pen that has acid in it that he can use to spray on bars and dissolve them. Now, why is he carrying a gold pen? Well, that's because gold is one of very few metals that is not dissolved by most acids. So he just pulls out that pen, squirts some of the acid onto the bars, and waits for them to dissolve. And it always happens in a matter of seconds or minutes in the movie. Well, it's not going to happen that way in reality. If you had enough acid, you really could dissolve iron bars of a prison cell, but it's going to take a lot more acid than what you would have in a pen, and it's going to probably take a little bit more time than they show in the movies. So what you're seeing in the image here on the right is a small piece of aluminum. This would be maybe just a tiny little strip of aluminum cut from something about the thickness of an aluminum drinking can, soda can. And that piece of aluminum's been put into very strong hydrochloric acid. That's probably 50% strength hydrochloric acid there. That small piece of aluminum would dissolve completely in about 10 minutes under those circumstances. So acids, what is it we know about them? Well, some general properties that they have. Acids have a sour taste. So foods that you eat or beverages that you drink that have a sour taste, that's attributed to acid. Acid dissolves many metals. And then another property that we're going to add here is that acids will turn something known as litmus to a red color. So what you're seeing here in the picture is a piece of something called litmus paper. And this end right down here is what this piece of paper looked like originally. Now, what's going on here, it's just regular filter paper, but it's been saturated in a litmus solution, and that solution has been adjusted for pH. So in this case, the litmus paper it's essentially supposed to be a neutral. So when it is a neutral pH, and we'll talk about pH later in this chapter, that indicates that there's not an excess of one ion or the other, and that should be a violet color. So this is kind of a purpley violet color. Now the other end of it, down here, has been dipped in an acid solution. the litmus turned red. So they're saying that the litmus originally was blue or purple, and acid will turn it red. Okay, so for litmus, acid equals red. What are some examples of acids that you might be familiar with? Well, probably the most common acid found in a chemistry laboratory is going to be hydrochloric acid. Hydrochloric acid is used for many things. It's used in industry for cleaning metals. It's used as part of food prep and food processing. It's used for the refining of metal ores. It's used for cleaning, things other than metal. It's used a lot. Hydrochloric acid is also something you carry with you every day because it's the main component of stomach acid. The reason that your body's able to handle it is that you have a mucus lining in your stomach that is resistant to that acid. If you didn't have that lining, or if something happens to put a hole in that lining, such as an ulcer, then you start to know that hydrochloric acid is there. It starts to eat away at the lining of your stomach. Okay, but it's there because it helps to break down food. Okay, it helps to dissolve and break it down into components that our body can use. It also helps to kill bacteria that you might ingest through your food. Now again, sometimes you get too much bacteria, more than the acid can handle, but for the most part, you know, if you've got a little bit of bacteria or dirt on something, that hydrochloric acid can take care of it. Now, you probably have experienced that hydrochloric acid in your stomach at some point if you've ever had indigestion, because what happens is the hydrochloric acid in your stomach refluxes. It kind of bubbles up or boils up into your esophagus, which doesn't have as much of that protective lining, so your esophagus really knows it when it gets hit with acid. It starts to burn and it's painful. And you also may experience that sour taste from the reflux. A couple of other acids that are pretty common that you may be familiar with: sulfuric acid, shown here on the left. So H2SO4, you can see how it's put together here. So these will be kind of the essential components we'll look at later. And then nitric acid, HNO3. Okay, again, you can see the structure, but we want to focus on those protons, those hydrogen ions that are available on those acids. Sulfuric acid is the most widely produced chemical in the US. Its production in the US alone exceeds 36 million tons. It is essential to many processes. Both sulfuric acid and nitric acid are very commonly used in the laboratory. Nitric acid has a little bit more of a special use because it is what we call an oxidizing acid. Now notice, you know, they both have oxygens, but if you look right over here, the situation that we have with this single bonded oxygen that isn't bonded to any other atoms, that gives it a little bit of extra oomph to do some other things. We haven't looked at redox yet, but when you look at the chapter on redox, you'll see where that is coming from. Sulfuric and nitric acids are used in the manufacture of many goods, including fertilizers, explosive dyes, glues, on and on and on. And sulfuric acid is one you may have encountered in an automobile battery. So that's why you have to be so cautious with that. It contains concentrated sulfuric acid. Other acids you're probably familiar with. Acetic acid is one that you probably encounter quite often. Acetic acid forms if you improperly store wines or if you intentionally let wine go bad. It forms acetic acid, which is also known as vinegar. The word vinegar actually comes from the French for the term for sour wine. So when wine goes sour, it produces this acetic acid, which we get as that distinct sour flavor on the tongue. Now, acetic acid is a form of what is known as a carboxylic acid. A carboxylic acid is an organic acid which contains a COOH group. So it may be condensed as COOH, or you may see it more commonly written out like this. It's a carbon double bonded to an oxygen, and then it has this OH group here. That is known as a carboxylic acid. Those are very common organic acids. So that is a class you really want to get to know. A couple of other examples of carboxylic acids that you're probably familiar with. citric acid, and malic acid. So these acids, carboxylic acids, are very often naturally occurring acids. They can be found in or derived from living organisms. So citric acid, for example, is the main acid found in lemons and limes. So we know it as citrus fruits, citric acid. Malic acid is found in things like apples, grapes, wine. It's not as pungent, I guess, an acid as citric acid. We don't tend to think of it as being sour, but if you think about it, apples, grapes, wine all have a certain note of acidity to them. Conversely, if we have acids, we're going to look at bases. Okay, so for bases, what are the properties of those? Well, as opposed to having a sour taste, a base will have a bitter taste, and we'll talk about that more in a minute. Also, bases feel slippery on the skin, and then they have the opposite effect on litmus paper. So if we start with litmus paper here, and here's the dry part, so instead of starting with blue litmus paper, we start with red litmus paper, we can see that it turns blue. So the thing to really remember is that for litmus, blue equals base. And a lot of people find it a little bit easier to remember the B from blue, B for base, B equals B. That leaves red to go with acid. So if you need that trigger, if something is basic, it will make litmus turn blue or stay blue. If something is acidic, it will make litmus turn red or stay red. All right, so bases, we said, feel slippery. If you look at the products pictured here, every one of these products contain bases. And if you look at them, you'll also notice there's another general relationship that you can make, with maybe one or two exceptions there. These are all essentially cleaning agents. These are not things you would consume, such as the acids that we talked about earlier. Now the Maalox, the tonic water, yes, those are meant to be consumed, but those are not consumed on a regular basis. Those are kind of special cases. Okay. Now, why do bases feel slippery? We said they feel slippery. That's because they're reacting with the oils on your skin, and they're basically forming substances very similar to soap. They're reacting, with your skin, and they're making this slippery soap-like substance. Well, if it's making it feel soap-like and slippery, what does that tell us about soap itself? Soap itself is basic, tends to be a base. And it's slippery because it is basic. It's one of the characteristics of that. It kind of reduces friction on our hands. So household cleaning solutions like ammonia and bleach and things like that tend to be basic, and they'll have that slippery feeling as well. If you've ever spilled a little bit of household ammonia or bleach on your hands, you'll notice that your hands start to feel very slippery. Now, bases can actually be quite dangerous to handle because of that, because people don't tend to think of them as being dangerous and wanting to wash them off. If you get an acid on your skin, it burns, it itches. You want to get it off quickly, and so people will go wash. But with a base, it's just sort of slippery feeling, and they don't realize that anything is going on until basically that base has reacted with the oils and the acids in your skin and broken your skin down, basically, until you've got kind of a red spot or even an open wound if you have a strong enough base and leave it there long enough. So caution needs to be used when handling bases. We said that a base will taste bitter. Here's a couple of examples of bases you may or may not be familiar with. Coenine and caffeine. Caffeine you're probably familiar with. The other one, maybe not so much. Okay, now bases you don't tend to see in food a lot because of the bitter taste, and human beings have an aversion to the taste for bitter. Now, why is that? Why would we be attracted to things that are sweet and sour, but averse to things that have a bitter flavor? Well, the reason for that is probably an evolutionary trait. It's something that has developed over time because of the fact that a lot of bases found in nature are things called alkaloids. And these are very often manufactured by plants. These alkaloids that plants manufacture are often poisonous to us. That is how the plant is defending itself. It is producing something that will be a poison, so animals won't want to eat it. And over time, our species has evolved to realize that this bitter taste on our tongue is an indication that we're eating a poison. So the idea is your brain tells you when you taste something that's bitter, that's bad for you, spit it out. Okay, so the bitter taste is a warning to us. Now, doesn't always work. Sometimes a little bit of a bitter flavor is something that people actually enjoy or look for. So for example, coffee. Now coffee overall is pretty acidic. If you were to measure the pH of coffee, you'd find that it falls in the acid range. But if I had just the acids in coffee, it wouldn't taste like coffee to me. It would taste wrong because things in the coffee such as caffeine that are basic give that little hint of bitter flavor that sort of enhances the overall taste of it. And so coffee is an example where you might be ingesting a base. Some other examples of bases: sodium hydroxide, potassium hydroxide, sodium bicarbonate. Okay, the two that are most commonly used in the chemistry laboratory are probably sodium hydroxide and potassium hydroxide. Those are also probably the ones that you're going to find in modified form most often in your home. Where are they used? Well, they're used for the processing of petroleum, of cotton. Both are used in the manufacture of soap. Sodium hydroxide is used to manufacture solid soap. Potassium hydroxide is used to manufacture liquid soap, so liquid hand soaps. They're both also used in plastic manufacturing. Sodium hydroxide you may have in your home currently. It's the active ingredient for drain cleaners such as Drano. Sodium hydroxide reacts with the proteins and acids in things like hair clogs and other organic matter that contain those carboxylic acids we talked about to break them down. Another base that you may have commonly in your home is sodium bicarbonate, which is also known as baking soda. Also, so you may have it in the kitchen, you may have it sitting in your refrigerator to absorb odors, or if you take antacids, you may find it in your antacid. It's a common ingredient there. Helps to neutralize acid, stomach acid, relieves heartburn, gets rid of that so-called sour stomach. All right, so we've talked about characteristics of acids and bases, but we also have to look at what defines an acid or a base. What is it that causes those characteristics? And we already mentioned the idea of the proton, the H+. Now, this comes from what is known as the Arrhenius definition of acids. We're going to look at two different definitions of acid and base. The first one is Arrhenius. Okay. Now remember the whole litmus thing? Okay, so acids here, I'm kind of highlighting that in red in acid, blue in base. So you'll see the base is blue a little bit later. The Arrhenius definition of an acid is one that produces H+ ions, protons, in aqueous solution. So for example, if I start with hydrogen chloride, if I have hydrogen chloride on its own, it's a covalent compound, there are no ions in it. But as soon as I drop that into water, it ionizes. So I now have H+ ions and Cl- ions, hydrogen ions, chloride ions. At this point, I call it hydrochloric acid, only when it's dissolved in water. Now what happens is that proton is highly reactive. So that proton's looking for something to bond to react with. And what's in water? Well, water molecules. And we've talked about the fact that they have hydrogen bonding, they have special properties. What's going to happen is that proton, that H+, is going to bind itself to a water molecule, and it's going to form this thing over here, which is known as a hydronium ion, H3O+. Now, a lot of times people will talk about acid content as just being the H+ content, but H+ doesn't exist in water by itself. It will always associate with water molecules. So these two terms tend to be used interchangeably to refer to a hydronium ion. The more correct term is the hydronium ion, the H3O+. You can use H+ as well, and you just end up eliminating a water molecule somewhere in your reaction. Now, when we look at the molecular formula for an acid, very often we will write what is known as the ionizable hydrogen first. Not every hydrogen in an acid is available to come off and become an ion, to create an acid situation. So for example, if we look at something called formic acid, and this is a very interesting acid, it's actually found naturally in ants. Ants produce this, used for the production of formica. So formic acid, formica, that fluorine, that's the acid that it uses in its production. If we look, there are two hydrogens in formic acid. The first one is an ionizable hydrogen, so it basically is able to come off as an H+. The rest of it, this hydrogen over here in the CHO2 part, is non-ionizable. It's within the structure of it. So we represent the structure of formic acid like this. We show the connections and the bonds using a Lewis structure so that we can identify where the ionizable hydrogen is. And it's actually the one that's attached out here to this oxygen, not the one that's attached to the carbon. That one doesn't come loose. This one will form an ion. The structural formula will indicate to us how the atoms are bonded together, and then we can use that to look at the placement of the ionizable hydrogen. A molecular formula simply indicates the number of each type of atom that's in there, and it may or may not give you information about whether or not a hydrogen is ionizable. All right, now what is the Arrhenius definition of a base? Well, this is something that produces a hydroxide ion when put into aqueous solution. So here we start with sodium hydroxide, we drop it into water, and we end up with just a bunch of ions in here. Okay, completely dissociates. Nothing but ions in there. Now, molecular compounds that contain an OH group, such as methanol, where I've got a carbon bound to 3 hydrogens and then the carbon's also bonded to an oxygen which has a hydrogen, these do not dissociate. So these are not bases. Okay, there's only particular cases. It has to be an ionic compound that will dissociate in water to form a base. Now, with the Arrhenius definition, acids and bases will naturally combine together to form water, and they neutralize each other in the process. So we talk about acid-base neutralization. The proton that's created by the acid combines with the hydroxide that's created by the base, and we get water, which is considered to be neutral. Now, there's another definition for acids, known as the Bronsted-Lowry, which we're going to look at in a minute. So we're just going to do a really quick comparison here. Why do we need two definitions? Well, it's because the Arrhenius definition is okay as far as it goes, but it doesn't explain everything. In particular, it doesn't explain why there are some substances that can act as bases, even though they don't contain any hydroxide at all. Okay, Arrhenius depends on a base to have hydroxide, but we have things like ammonia, NH3, household ammonia. Okay, if we look at that, we know it's basic, it has all the properties of a base, but there's not an oxygen in there. How are we going to produce a hydroxide from that? Okay, the Arrhenius definition does not apply to non-aqueous solvents. We have to have water in order to have that hydroxide there as well. So, the definition that is applied to a broader range of acids and bases is the Bronsted-Lowry definition. And that's the more all-purpose one. It's a little bit more difficult to spot acids and bases sometimes, but it applies to just about anything that will act as an acid or a base. Now, what happens in this definition is that instead of focusing on whether or not something has a particular ion, we're just going to look at the transfer of those protons, those H+ ions. All we need is something that produces a proton, and then we watch where that proton goes. Okay. Now, when we say it's a proton, by the way, H+ is a proton because if we look at a hydrogen atom, in the ground state, a hydrogen atom has 1 proton, 1 electron. But we've taken the electron away to make it a positive ion, so there's nothing but a proton in the nucleus. Okay? So this definition is then going to focus on the idea of something that donates an H+, a proton donor, and then something that accepts it, a proton acceptor. So what gives up the H+? and what takes it in. In the Bronsted-Lowry definition of acids and bases, an acid is going to be a proton donor, a base is going to be the proton acceptor. Okay? Now, the reason it has the name Bronsted-Lowry, these two gentlemen actually didn't work together. Bronsted was in Denmark, Lowry is in England, but they developed it independently and simultaneously. Their results appeared at about the same time, so the name gives credit to both of those scientists that worked on this idea. Now, according to the Bronsted-Lowry definition, hydrochloric acid is a Bronsted-Lowry acid because when we put it in solution, it donates a proton. So HCl plus H2O yields a hydronium ion, so the H plus from this bonds to the water, and then it leaves us with a chloride ion. Now, this definition, as you can see, it more clearly accounts for what's happening to the proton from an acid. It's not just being produced in water and floating around, it's showing that association with the water molecule, which we said it always does. It forms that hydronium. So the Bronsted-Lowry definition relies more heavily on using hydronium rather than just H+. Now, where does Bronsted-Lowry really shine? Well, where it works is with things such as that ammonia that we talked about, bases that don't appear to contain a hydroxide ion. They don't, okay? There's no hydroxide in them, but those things still produce hydroxide when we put them in solution. Why is that? Well, that's because if we can think of water instead of H2O as that HOH, remember we said that hydrogen and hydroxide come together and neutralize one another. So I've got an H plus and I've got an OH minus, and those can actually come apart. Well, what happens is this thing, ammonia, is a proton acceptor, which is what we said a Bronsted-Lowry base is. So that H plus can come over here and it forms an ammonium ion, NH4, and now in the process the water is what's getting turned into the hydroxide ions. That's where those are coming from, and that's what makes it a basic solution. So it's important to realize that when we have acids and bases, those are going to occur together. It's just like when you have cations and anions. You're not going to find cations without anions. In Bronsted-Lowry, you're not going to have a proton donor without having a proton acceptor in this sort of acid-base reaction. Okay? So if I look at it here, in this situation, reaction between hydrochloric acid and water, this is going to be the proton donor. It's going to give up an H+. This one's going to be the proton acceptor. Now when I do that, I end up with something over here and something over here that have different characteristics. Now when I look at the ammonia, we said that this one was the acceptor and this one was the donor. So the ammonia becomes the base, the water becomes the acid. Notice water here is playing a dual role. Depending on what we put in it, it can act as either an acid or a base. We'll touch on that more in just a second. Okay. But now when I do that, if I look at what I have on the other side, I have something now, ammonium ion, that if I were to take that ammonium and reverse the reaction, see these arrows here, how they go in both directions? This means the reaction can proceed from left to right, but it can also go from right to left. These two things, NH4 plus and OH, will react to take me back to the original products. And that's happening on a certain scale, going in both directions. When that happens, this one is donating the proton, so it is also considered an acid in that case, and it's known as a conjugate acid. So I have an acid-base pair. Ammonium is the conjugate acid of the base ammonia. Hydroxide is going to be the one that accepts the proton from the ammonium. Okay, so it is known as the conjugate base because it is what is formed from the loss of the proton from the acid over here, the water. So I have another acid-base pair, acid with its conjugate base. All right, so we said that water can act as an acid or a base. So it can accept a proton, it can donate a proton. Water's not the only thing that can do that. If you have a substance that does that, that acts as an acid or a base depending on the conditions, this is known as an amphoteric compound. All right, so for instance, we said the original reaction we had, ammonia plus water formed ammonium plus hydroxide. Now let's flip that over. Okay, so now this one was the proton acceptor. It accepted the proton from the ammonia. This one was the proton donor. It was originally water. Okay. Now, when we flip it around, ammonium becomes the proton donor. In order to go in this direction, okay, it has to act as an acid, and then hydroxide has to act as the base. So what was the base becomes the acid, what was the acid becomes the base. That's how we tie them together as conjugate acid-base pairs. So, for instance, ammonia and ammonium, there's only a proton difference between them. That's a conjugate acid-base pair. So we looked at the ammonia-ammonium. Water is the same way. If we take an H2O and remove a proton, we end up with OH. So H2O and OH are a conjugate acid-base pair. And similarly, H3O plus and H2O. This is also a conjugate acid-base pair. Okay, conjugate acid-base, that's supposed to be an A there, CAB. So now we can start to look at these reactions and determine if something's going to be an acid or a base and what its conjugate will be. So if I'm starting here, I have H2SO4, H2O. We know that water's amphoteric, so let's focus on the other one. Excuse me, H2SO4, if we look at the structure of it, I'm not going to draw it out here, but you can draw the Lewis structure, you'll see that it has two ionizable protons on it. So this one's more likely to donate those protons. It will act as the acid. That leaves water to act as the base and accept it. Now, what happens is I only give up one at a time here, so only one proton is going to come off. So here I went from H2SO4 to HSO4. I have a net negative charge now. This becomes the conjugate base of the acid that I started with. The water accepted the proton that was given up, so I get an H3O plus. This becomes the conjugate acid of the base that I started with. Okay? So now we can look at acid-base reactions. We can label things on the reactant side as either acid or base, based upon the Bronsted-Lowry definition. And then we can look at the materials that are being produced on the other side. We can look at the products, and we can label them as the conjugate base or acid of the original starting materials. Again, the reason we want to emphasize this is because there are so many naturally occurring reactions, organic reactions, that rely on acid-base. You're going to be seeing a lot of these. This is heavily used in industry and in the production of materials. So understanding acid-base becomes very important. All right, so that's the start to chapter 14. In the next two sections, we'll look at some reactions of acids and bases, and we'll look at the idea of an acid-base titration, which gives us a way to actually quantify how much acid or base we have in a solution. Again, this is a very common laboratory technique that's used in the analysis of these sort of reactions and syntheses.